As introduced, I'll be talking about the geometry of non-planar on-shell diagrams and also some of the properties that have to do with the corresponding differential forms. This presentation is based on some ongoing work with some of my collaborators at UC Davis, including Yara, my supervisor, who's there in the back. In order to get started talking about this topic, first I wanted to review a little bit, very broadly, what on-shell diagrams are. So on-shell diagrams look something like this, where we have white and black vertices, and they encode information about a particular amplitude. And the way that the white and black vertices can be interpreted is as putting some constraints on external kinematic data. So here, lambda and lambda tilde are spinor helicity variables with particular constraints. Very quickly, we will get rid of sort of this physical motivation and focus mainly on the mathematical objects that come out of it, which are the corresponding differential forms, which you can get in a variety of ways, one of which is by doing some boundary measurement procedure on these diagrams. This is something that is pretty well understood for planar diagrams, for which we find that the pole structure of the on-shell form corresponds to the boundaries of the positive Grassmannian. Really, this on-shell form corresponding to the diagram, the one that is necessary to compute the amplitude, is the canonical form of the positive Grassmannian, which are matrices that are k by n, that with real entries, positive minors, and you have some GLK invariance encoded. And here I just have two very simple examples at 4 and 5 points of some planar on-shell diagrams, and specifically these are in the MHV sector, where we have the appropriate number of black and white vertices, appropriate number of helicities for the particles, that we end up in with k equals 2 for the Grassmannian. And so the differential forms involve these Park-Taylor factors, where it's just 1 over consecutive Plücker coordinates, or consecutive minors of our 2x4 or 2x5 matrix. What we would like to do is to generalize these ideas to non-planar diagrams, and to make sure that that's not too hard for us, we'll stick to the MHV case, where things simplify a lot because it's a lot more restricted. So, the nice thing about the combinatorics of MHV diagrams is that you can actually describe the entire diagram very straightforwardly by just looking at the black vertices. What you can show by doing some counting argument to do with how k, n, and the constraints depend on the number of black vertices is that they're exactly n minus 2, where n is the number of external edges, and each black vertex connects to 3 external edges through some white vertices. So for this square, which is our very simplest diagram we could possibly have, we can describe it by saying that one black vertex is connected to 1, 2, and 3, and that the other black vertex is connected to 1, 3, and 4. And this gives you a complete characterization of the diagram, and then we can use this combinatorial object, sort of this set of triplets, in order to continue and do some computations. For the 6-point diagram, which we'll see a lot, since this is one of the first really non-planar diagrams that we can see, it'll appear a lot in examples, and here's a set of triplets for it.
Okay. Artem, before you move on,
yeah.
So this n equals 2 black vertices, this 2 is the k equals 2 for MHV? Change or no?
So there's n minus 2 triplets. So if you have n vertices, you end up with n minus 2 triplets. But it's not that it's n minus k is the correct formula. It's specifically for k equals 2. There is a counting argument where you can restrict it in this way. I think if you have a higher k, you actually end up with more black vertices rather than less, and the black vertices can sort of be nested inside of the diagram. You don't have something this nice where every black vertex really sees external edges in this way. Yeah. So,
Are there further constraints on the triples here?
Yes, there are some further constraints which are necessary in order to make sure the differential form doesn't vanish. I might comment on that on the next slide, since you asked, since it's a little easier to see once you know what the differential form looks like. But generally you want the diagram to be connected right? If it's disconnected, then it sort of factorizes in some way. And it has to be sufficiently connected that you don't have maybe like two external legs connected to the same vertex at the outside.
Okay, so there's some notion of being like reduced.
Yeah. So there's a notion of reduction, and requiring that the diagram is reduced is part of what goes into this argument. That's right. Okay, so we have these differential forms which can be computed from the triplets. So if you have the form from a particular triplet, from a particular set of triplets, you have these factors coming from all of them and some constraints coming from the matrix in the Grassmannian. And as we try to analyze this form, there are sort of two directions you can go in terms of making the formula a little bit more precise and putting into a standard notation. So one of the nice things about the MHV case is that the Grassmannian matrix, which is 2 by n, lives in the exact same space as your lambda spinor helicity variables, where if you take all n of them, they're all 2 vectors. They also are a 2 by n matrix. And one of the constraints is that they actually end up being sort of parallel to the matrix in some sense. And you can convert these delta functions to ones that involve lambda directly in this way. If you do this through some gauge fixing procedure, then you end up with a determinant in the numerator. And one of the ways you can sort of require that the matrix is reduced is by making sure that this determinant doesn't vanish. It sort of puts some extra constraints on what triplets are allowed. Another approach, which is where the geometry will come from later, is to do a decomposition of this differential form into Park-Taylor factors. We know from before, from the planar diagrams, that Park-Taylor factors correspond to the positive Grassmannian, so we already have some idea of how there's a geometric interpretation, and that's what we'll get from this approach. So this was my brief introduction on shell diagrams and the combinatorics that get us to MHV. And this is my plan for the rest of the talk, where I will discuss each of the formulas in a little bit more detail and say what you can do with them and hopefully make some more precise statements that you will believe along the way. Okay.
So,
Yes.
I want to consider MHV for
Yes.
the talk.
Yes, everything I'm doing is MHV, but with no restriction to planarity. Yes. Okay. So for the determinantal formula, what we are going to use this for is sort of seeing what diagrams are equivalent to each other. Before I get to that next slide, just to motivate this, we know from the planar case that we have a square move accessible to the diagrams, where you can sort of rotate a square of alternating white and black vertices and gives you a diagram with an equivalent form. And even from the mathematical side, in the boundary measurements, sort of from Postnikov's paper, you know that these moves are important. You sort of have equivalence classes of diagrams. It turns out that for non-planar diagrams, you have a larger family of moves for us to consider. Okay, so here's the determinantal formula that I wrote down before in a little more detail. The way that you actually find this matrix to take the determinant of is also constructed from the triplets. Using the triplets, you construct a matrix like this one, where each row corresponds to a triplet, and the entries are sort of the two indices that are not the index corresponding to the column. So if you have a triplet 1, 2, 3, you will have 2, 3 in column 1, 3, 1 in column 2, 1, 2 in column 3. And as part of the gauge fixing procedure, you need to choose a basis in which you sort of do an inversion of those delta functions, and you find that you erase 2 columns of this matrix according to whatever basis elements you chose, and you end up with a square of that in the numerator. So here, one choice you could possibly make is you sort of remove columns 1 and 3. Taking the determinant of the remaining result, you're forced to have 3, 1, and then you have a couple of options here. You divide the 3, 1 out, and so you're left with the square of this sort of polynomial of Plukers, and this is the appropriate differential form for this on-shell diagram, just coming from sort of physical notions of how we expect the constraints to come together. Right. So here's a theorem I'm going to state, and I'm going to explain the pieces of it as we go on. If we have 2 different sets of triplets, or really you can say 2 different diagrams, the following statements are equivalent. The sets of triplets are related by a sequence of sphere moves, which are the generalization of square moves I was talking about. The corresponding forms are equal, or the corresponding doublets, which are sort of less redundant combinatorial object, kind of like the triplets, but encoding more precise information. The doublets are equal to each other. Okay, so here's the square move, in case you haven't seen it before. You take the square and you rotate the black and white vertices around. And an important thing to note is it doesn't just apply to this specific diagram, it also applies if this sort of square appears as a sub-diagram inside of something bigger. So anytime you have a pair of triplets that sort of share two indices, so here 1, 3 is shared, you can rotate it around so that a different pair of indices is shared, and the corresponding form does not change. Sphere moves, which apply to non-planar on-shell diagrams, describe a set of triplets that together triangulate a sphere. So it's sort of hard to draw this kind of thing, at least I didn't quite take the time to really make a 3D image, but if you have this 6-point diagram where I've removed the external legs just so that they don't get in the way, but you have these white vertices labeled, what you can imagine is that each of the black vertices corresponds to a triangle in the triangulation of the sphere.
Just an octahedron that's bicolored.
Yeah, exactly. It's an octahedron that's bicolored.
Yeah,
I didn't make an image of an octahedron in quite that arrangement. Yes. And so if you take the triangles of the second color you have, that gives you a second set of black vertices. So here it's corresponding to the white triangles. And what you can show is that these two choices for black vertices will give you equivalent forms. The square move itself is also a type of sphere move. It's just the simplest possible one. If you take a tetrahedron and triangulate it, then you end up with the square move. Okay, so here we have sphere moves. The next ingredient we had was doublets, which I don't have time to cover in this presentation quite how you can motivate them, but one of the ways that sphere moves are proved is by sort of considering all of the possible pairs of indices that appear in each triplet. The way you can define the doublets is just as all of the pairs that appear in an odd number of triplets. So if it repeats multiple times, you sort of count how many times it repeats. And for our square, you end up with the doublets being just 1, 2, 2, 3, 3, 4, 4, 1, it should be. Sorry about the typo. And if you sort of switched the vertices around on the square, then you end up with exactly the same pair of doublets. It would still be sort of this cycle all around. Same idea for the 6-point diagram. You have a longer list of doublets, but they don't end up changing when you do the sphere move. Finally, when we are talking about the form and making a connection to the doublets, there's a very neat result to do with the factorization of it. So it's a little bit lengthy to state, but the idea is that if you have a set of triplets describing some diagram, and in that set of triplets, there's a subset that itself corresponds to some diagram, then you can factorize the resulting differential form. There's some caveats about when this could be useful. It technically always works, but if you just remove one triplet and then add it back in when you're factorizing things, you might end up canceling things out with that extra factor. But a lot of the time, this factorization procedure can explain when you have extra terms in the numerator. This is actually the only way that linear terms in the Plukers can get added to the numerator. Most of the time you'll have squares of those polynomials, as we saw for the larger determinant. So here's one of the simplest cases that you can see this from. I have this 5-point diagram. This triplet includes an index that isn't included anywhere else, so you can factor it out. You have the remaining part of the diagram, and then you need to multiply by a correction factor to do with the external edges that are shared between the two parts that you sort of factored this into. And so this, especially when the diagrams get a lot more complicated, gives you some factorization procedure into irreducible pieces. And it has a lot to do with the factorization of the numerator, since the denominator is often the simpler part of these diagrams. And there's a lot of more involved mathematics to do with studying like the vanishing locus and factorizations of it. Okay, the way that we show this factorization is the determinantal formula. So here I did my best to, yes?
Can you go 1 second to the research? So, could I consider 2153 also as a subset?
Yeah, you could. And so there's the factorization is not necessarily unique. Yeah,
Okay.
that's true.
And sorry, is it the 5 that's like makes it reducible here? Or? Sorry, what was the combinatorics that makes this reducible?
This is reducible because you can find a subset of the diagram, so a subset of the triplets, that is itself a diagram that contains some new index. Here I chose to factor out this triplet, 153, but with this diagram it's actually quite symmetric. You could choose just about anything. I could have taken like 134, and that itself is a sub-diagram. It contains an index not contained anywhere else. And I could factor out like 134, and that would be left with a square here, which would be 1, 2, 3, 5. And these are just different ways of factorizing this form into sort of smaller pieces.
And what does it mean that R corresponds to some diagram?
I guess most importantly, it means that the number of indices in that subset is 2 more than the number of triplets. Because a diagram always has n indices, n minus 2 triplets. So factoring out one triplet always works, but most of the time you'll be factoring out some bigger irreducible piece. For example, you could find this diagram somewhere inside of a bigger one, and you'd be able to factor it out.
When you say factoring out one triplet always works, do you mean you can always find an index which shows up in exactly one triplet?
No. So if you have an index that appears in exactly one triplet, then that triplet could be factored out, and you would factor it out with an associated linear factor here. And in particular, since this triplet is 1, 3, 5, 1, 3 appears in the denominator of this triplet, so it really corresponds to just adding 1, 3 to your numerator in some way. And so if you have linear factors present in the numerator of your form, then it has to do with this kind of factorization.
Did you say the factorization is not unique? Because that example doesn't show it, because I could factor out the 4 now. And
Yeah, the factorization is not unique.
But this example doesn't show that.
Well, starting from this step, I could have chosen to factor out any one of the 3
But
triplets.
if you make all the choices, in this case, you're always going to get the same answer.
You will always get the same form, but like the choices are different. I guess maybe I don't understand the question.
I guess I was expecting unique factorization to be if you've broken everything into irreducible pieces, then the pieces.
The thing is that part of the way that this factorization procedure works is on the parts that are overlapping, you need to sort of glue back in these correction factors. And I think depending on what order you factorize things, these correction factors might end up being different. There's sort of a choice to make with what polygon you glue on, which here doesn't happen. Maybe this isn't the best example because it only overlaps on 2 indices. But I don't think in general you can make some like uniqueness statements about the factorization. Maybe with some more work there's some canonical way to do it, but that's not something I've thought about too much.
And there's also some connection of these triples to circular extensions, right?
Yes, so I'll get to circular extensions. That's actually a lot more relevant to the decomposition formula because it's really these circular extensions are really how we find the Park-Taylor factors we can decompose this bigger formula into. That's right. Okay, so the way that the factorization can be shown from the determinant formula is that if you have this subset of triplets that corresponds to some smaller subdiagram, then the matrix that you're taking the determinant of is sort of like block triangular, and you can really factorize the determinant in a particular way, provided you add back in these triplets P to make sure that the second determinant also corresponds to a valid diagram. So I know it's a very brief sketch, there isn't that much time in this presentation, but the determinant formula helps make this factorization happen. And so going back to the theorem, that I stated earlier, sphere moves imply that the forms are equal just by how the sphere moves were found and constructed. There's a pretty direct proof of that. The forms are equal implies that the doublets are the same, because if you perform this factorization procedure and reach irreducible pieces, whatever they may be, it doesn't matter whether it's even or not, the irreducible pieces always have the same doublets, and gluing them together just by reversing this factorization keeps it the same. And there's a neat sort of Euler characteristic combinatorics argument, which I don't have time for, that shows that equal doublets imply that you actually are really performing things on a sphere. So if you weren't on a sphere, then you would have some inequalities that don't match for your Euler characteristic. Okay, so with the 10 minutes I have left, let's move on to the second half, where we're going to be speaking about these geometric notions. So here's the formula we had for our differential form as a sum over Park-Taylor factors. And so these triplets define some partial cyclic order on the set of indices, and this sum is over the extensions of the cyclic order, if you'd like. Where here I wrote it as the set of permutations up to cyclic shifts, just in case sort of cyclic orders aren't something people have heard of. For this example, at 5 points, we have 1, 2, 3 in order, 1, 3, 4 in order, 1, 3, 5 in order. Modulo cyclicity, we can decide to just put 1 as the first index, and these two permutations end up being the ones that are extensions of these three triplets. And so the differential form can be expanded into these two factors, where this would be the differential form if you added them together and did some partial fraction identities. Now, what we can do is we know that each of these two pieces are Park-Taylor factors, and they should have some geometric counterpart in terms of a positive region that looks a lot like the positive Grassmannian, except we can take this positive Grassmannian and maybe flip the signs on some of the columns, do whatever we want to try to make it into a nice looking region. There's actually a lot of ambiguity with how you define these positive regions, where here, the way I've written it, I have a positive region where I have indices that sort of tell you the ordering of the minors, but you can also have plus or minus signs that sort of flip the signs on some of the minors as well. And these positive regions together give you all the possible reflections of the positive Grassmannian, which would be just the naive ordering just from 1 through n, all with positive signs. And there's a lot of nice properties that these positive regions satisfy. If you take the last index and move it to the front and add a minus sign, it doesn't actually change any of the inequalities. So this notation is a bit redundant. One way to fix this is to always keep rotating things until 1 is the first index with a plus sign. These positive regions geometrically are connected on a codimension 1 boundary if two adjacent indices are swapped with nothing else changing in between. And so by the end of the presentation, we will make some statements about when these regions actually end up being connected. And most importantly, these positive regions, no matter what the signs are, the canonical form is the Park-Taylor factor. And so knowing that our differential form has this decomposition to Park-Taylor factors, we can try to guess what triangulations we would prefer. So there's tons of options for each Park-Taylor factor. We can choose whatever signs we want, but we want to try to make the best choice. So the on-shell form for an MHV diagram with some triplets is a canonical form for pseudo-positive geometries defined by these triangulations, where we've made some choice about what the signs of each of these simplices are. And the goal for most of the rest of this presentation is just to show a lot of examples of what these spaces are. Largely without pictures since they're high dimensional, but hopefully I can give you some intuition over what things look like. The first example I have here. Yes?
What do you mean by pseudo-positive geometry? What is that for you?
Good. So a positive geometry is one that has a canonical form that never vanishes on any of sort of the recursive residues that you can take. But it turns out that that is actually too strong of a requirement to make in these cases. What you can show is that if you have a triangulation of some geometry, you will at least have a pseudo-positive geometry where the form vanishes on some of the residues that you may take to the boundaries. So somehow these Park-Taylor factors, they collude to vanish on particular facets of the geometry you end up with, and it turns out that no matter what choice you make, you can't get rid of this property. Sort of the numerator has a vanishing locus that intersects the geometry on some of the places. And you just have to deal with that and maybe try to figure out if there's ways to make the geometry better behaved on like lower codimensions, because maybe you want the first boundary, so the first residue you take, to always be non-zero. So there's some options to take with that.
So what does it mean physically?
What does it mean? What does it?
Does it have a meaning?
I wouldn't be able to give a physical meaning to it off the top of my head. Okay, so here's our square, where we all know that we can associate to it the just G plus 2, 4, the positive Grassmannian. But if we change the orientations of the sum of the triplets, then we end up with a different set of cyclic extensions, and it gives us a different geometry to associate with this that happens to have the same canonical form. And well, up to a sign at least. So the canonical forms are equal up to a sign, and this highlights how there's choices, and maybe this choice is somehow worse than the other one. This is an example of a pseudo-positive geometry, because you can see that each of these positive regions has 1, 3 as a boundary, but 1, 3 is not one of the poles in our differential form. So it has a vanishing residue on this boundary, and we would prefer not to have a geometry like this if we could make some choice about it. At 5 points, if we have this set of triplets, we have this pair of extensions, and having spent some time trying to come up with some intuition for what these spaces might look like, we came up with this kind of picture where this is a 6-dimensional space, and so here I have sort of a projection onto something much lower dimensional. At the top, so the two positive regions actually connect to each other with some non-trivial topology, where they connect at some point where if you imagine that the columns 1, 2, and 3 vanish in your matrices, then you just end up with a single point that both of these positive regions can reach. But if the minor 4, 5 vanishes, then the two of these also agree, because the only difference between them is whether the minor 4, 5 was non-negative or non-positive. And so you kind of have this high-dimensional pinched torus for this geometry, and this ends up being a pseudo-positive geometry as the differential form vanishes on some slice. What you end up seeing is that if you go to like a second codimension facet, it ends up being a circle around this torus, and we know that there are results about showing that on a circle, the canonical form is 0. It's not a positive geometry, and so the appearance of such facets on this geometry end up giving it this pseudo-positive characterization as well. When we go to a 6-point example, things keep getting a little larger. This one, the topology of it, we haven't fully taken the time to figure out. I think when we computed the Euler characteristic, it was like -2. So it has even more handles associated with these kinds of pinched points. And one of the things I would like to point out in preparation for the last result of the talk is that despite having all of these positive regions, they all still end up being connected through swapping these adjacent indices. So when you swap adjacent indices, that means a boundary is shared. And these different positive regions have a structure that is kind of like sort of the octants of an octahedron, where on the left everything has 3, 6, on the right everything has 6, 3. You have 2, 5, and 5, 2 in alternating rows, and sort of the top ones have 1, 4, while the bottom ones have 4, 1. And so it's really glued together on all of these codimension 1 boundaries. And one of the things we were interested in is, can you always find this kind of very connected space when you are making the choices of what geometry you correspond to your form? And it turns out that the answer is no. When you go to a 7-point example, so this is some 7-point irreducible diagram, you have this very long list of positive regions that you end up with, and here each row is its own codimension 1 disconnected piece. So you can see that in the first row you sort of have like 6 swapping with 1, etc. And you can go down the list and check that each row doesn't connect to any other one, no matter what choice you make for the signs. So there's sort of a limitation for what geometries are possible, and you end up with these somewhat disconnected pieces. They will always end up being connected, but only at sort of these pinched points or pinched line segments, because if you go enough codimensions down, you do reach places where the boundaries match. You just won't always find it on the first codimension.
So, did you get the Euler characteristic here?
I could on demand, but I don't have it off the top of my head.
Because in our delta algebra paper,
Yeah.
we found an example that at n equals 7, there was one that did not embed on the surface.
Yes, this is exactly that example. Yeah. So the idea, and that's what I will get to, is that this diagram, the reason it doesn't work is to do with it not being able to be embedded on a sphere. So earlier I talked about sphere moves, which appear when a diagram, after you remove the external edges, can be embedded on a sphere, and it turns out that is relevant to this story of connectedness as well. For any internally planar diagram, so you remove the external edges and check whether the remaining parts are planar, there exists an associated codimension 1 connected geometry that is related to the planar embedding. So if we have this 6-point example that we had before, if you embed it in a plane like so, and you can choose the orientations of the triplets to match the planar embedding. So you sort of go counterclockwise around each triplet. This defines an orientation for you. And these resulting extensions will have this connected property where you can swap adjacent indices. And so somehow this notion of the diagram being spherical is related to the moves, and it connects to this ideas in the geometry.
So the higher the genus, there's some interpretation here.
It's not even the higher the genus, it's just if you go beyond genus 0, things start to break down. We sort of had some leeway because this diagram is non-planar if you include the external edges, but somehow the external edges behave differently when you start looking into what the corresponding form and geometry look like. I wanted to give you a quick sketch for how we prove this. So the goal is to show that the regions are connected by swapping adjacent indices. And one of the ways to do this is by studying these extensions by breaking them into different sectors for you to consider. So we split it up into different sectors that are each defined by some poset. So these triplets, we had some cyclic rotations we could apply to them. If we fix these cyclic rotations, then we can sort of split these into groups. And then showing the connectedness within each group is pretty straightforward. You can just look at the poset and check that all of the linear extensions of it are connected to each other. Showing that the different posets are connected to each other is a little more subtle, but there's a pretty beautiful bijection to perfect finding connectedness of the graph of perfect matchings of planar graphs. So the reason that planarity ends up being a requirement here, at least with this approach to proving it, has to do with some seemingly unrelated result of perfect matchings of planar graphs. But it ends up being one of the ways to approach it. Okay, so to wrap up the talk, the 3 things I just sort of tried to give you and motivate: equivalent on-shell forms have this characterization in terms of sphere moves and doublets. On-shell forms are canonical forms of some large family of pseudo-positive geometries, which one would like to explore and single out some preferred geometries on which you can work. And in particular, one of the special ones that we might want to prefer is if the diagram is internally planar, there are some strongly connected geometries that you end up with. And the directions that one could keep going in is to see if there's more properties, to learn about these geometries, to single things out, maybe keep looking at the Euler characteristics, especially for these really non-planar diagrams. It's kind of unclear what to do with them because we can't use the connectedness in order to single out what the right choice is. And since all of this has been working in MHV, hopefully there's some lessons to learn to generalize it beyond this sort of toy case where we had all of these triplets to simplify things. Yeah, thank you.
Thank you for this very nice talk. More questions?
There's another Euler characteristic that's fun to look at here. It's if you take the scattering potential in the CHY formula and take a hypertree and set to 0 some of the edges in that which do not appear in the hypertree, then you get an Euler characteristic in M0n. And so that, if you look at that for just a totally planar graph, that Euler characteristic is going to be 1. Okay. So, but if you take some more complicated hypertree, the Euler characteristic increases. Like for the octahedral leading singularity, it bumps up to 2. So yeah, I mean that's another interesting Euler characteristic to look at.
Not something I have thought of, but yeah, there's tons of topological properties to try to consider. That's right. Yes?
So more basic, but so from going from planar to non-planar diagrams, what kind of physics are we describing?
It's sort of describing a more general limit that, well, you're removing a limit that is usually taken. So these on-shell diagrams correspond to n equals 4 super-Yang mills, where it is very common to take the large n limit, where you have a large number of colors, which forces the planar diagrams to dominate your expansion.
Capital N?
Right, there's a lot of n's there. If the number of colors in your super-Yang mills becomes very large, then when you do computations of the amplitude, planar diagrams end up being the dominant term. And so as it goes to infinity, planar diagrams are the only thing relevant. But if you want to step away from this limit and sort of consider a more general amplitude for some colors, you need to start understanding these non-planar diagrams. So really in physics, physics doesn't usually distinguish on what the topology of the diagrams is. So it's just some special cases that the planar diagrams embody.
A large number of colors, like for each particle there are 3 colors or something like this.
So in QCD, so the quarks, gluons, the standard model, there are 3 colors, but the physical theories that are described here are more abstract, where it's something that it's a parameter that is controlled as you try to understand the amplitudes. Yeah. Yes?
Is there any sphere move that's not the square move, but exists in the planar world?
No. Yeah. So
No,
this
definitely not.
Yeah, the square move is the only one. So you can sort of combine square moves into like retriangulating anything you want, but everything can be built out of it.
No questions? Okay, I don't see any, so let's thank the speaker again.